Hello everyone, welcome back to another video in the LLMs related playlist. In this video, I'm gonna show you all how you can pre-train your own LLM, that too in 1 bit, with the help of this paper, the era of 1 bit LLMs. The results which I got after pre-training was pretty good actually, because I wasn't expecting that good result, and I can say that whatever potential is said in this paper is true. If you can, complete your pre-training following this approach itself, you're gonna get some great results for sure. So now in this video, I'll explain this paper. I'll also show you the code of how you can pre-train, and I'll also show you what were the results I attained. As you can see here, I started with a loss of 7.66 and ended up with a loss of 3.4. And this is pretty good because I trained it only for 5,000 steps, and that too in Google Colab, actually with a reduced model size. So for that, I think this is a very good performance. And I also tested it with some other model as well, and it gave pretty good results. As you can see here, the epoch was going, the learning rate got reduced very well, and the loss was pretty good actually. It surpassed my expectations. I was expecting a loss of 5 or 5 point something, but I got it around 4 itself. So let's start with the explanation of the paper first, then I'll show you the code, and then we'll see what can be done next to take this model to next level. Okay, so recent research such as BitNet, which was long time before, said that 1 bit LLMs are very good, and it can match the performance of the original float present 16 LLMs with, the closest, not exactly the same performance, but it can come close to the performance of that FP16 model. That is what was said. And when you convert this model to 1.58 bit, right, the perplexity was same or close enough. Perplexity, if you see, is evaluation metric where the perplexity should be less, like where the name suggests perplexity, like how confused is the model. When your model is less confused, which means your model is doing good, so the perplexity should be very less. And this model was very amazing in its size actually. I trained only a 70 million parameter llama model, and that was having a very good response. So stay till the end to know how you can pre-train this model and how we can go forward. Now let's check on this more profoundly. The 1.58 bit LLM defines a new scaling law and recipe for training new generation of LLMs. That is what is the key here. The 1.58 bit LLMs define a new scaling law and recipe for training, because whatever was said in BitNet was pretty good, but to make the weights quantized, right, they gave some novel approach, and that was pretty good actually. So given a weight, like this 0.2961 minus 0.0495 minus 0.4675, whatever it is, it will be converted into this weight. Only 1 minus 1 1 0. Okay, 1 0 minus 1. This is the set it has. Other than that, it wouldn't have anything actually. So by this, what happens is, usually when you have a weight, right, you'll multiply it and then you will add it, right? That's what happens. First multiplication, then addition. That is what usually happens when you do a model fine tuning or inference, whatever it is. It will be wx plus b, right? W transpose x plus b. But here, since it is 1 minus 1 0, you are totally getting rid of multiplication, because if you multiply with 0, you're gonna get 0. If you multiply with 1, you're gonna get the same number. If you multiply with minus 1, you're gonna get the same number with an opposite sign. That's all. There is no multiplication, there is only addition. And that is what is known as a Pareto solution, and that has given a very good performance. It has reduced the inference cost, it has reduced the energy consumption, it has increased the throughput. Everything is good with this paper actually. This is an amazing paper, no doubt in that. So Recently, we have moved from 16 to 4-bit, and there is now a quantization method known as HQQ quantization as well. I'm exploring that. If I find it very awesome, I'll also let you know of how you can do that. It is said that like you can achieve almost or even better performance of what you get in 16-bit with the help of just 2 bits. That is what they are claiming in HQQ, and that is something very recent. But in bitnet they are using just -101. Okay, this is trinary, probably not binary, because you have by -1, but -1, it is just to indicate the sign. Okay, it is technically it is just 2-bit, 0 and 1. To give sign for 1, it is having -1, that's all. Okay, so that's why they are calling it as 1.58-bit. The advantages which you get with bitnet 1.58 is there are two advantages. Obviously, you have memory efficiency, you have computation efficiency, but the model's capability is stronger due to its explicit support for feature filtering. Okay, it is able to filter the features, so the modeling capability is very stronger than before. And it is shown, they have made some full experiments with bitnet, and it has shown that it can match the performance of full precision baselines in terms of both perplexity and in-task performance. In-task performance means your fine-tuned model. Let's say it is your QA, your summarization, whatever task you have, in those also this model has done very well actually. Okay, now coming on to the math, like this is the crux of the paper. That's all. Okay, this is the crux of the paper. This is a very short paper, as you can see. This is 8 pages. Here what happens is, when you give a weight, right, they are following a round clip mechanism where they'll clamp the weights to -1 and 1, that range, and they will divide the weight by the absolute mean. Okay, that is what they do. First they'll clamp it to -1 to 1, and then they'll divide it by absolute mean. In previous paper, which is bitnet, what they did was, bitnet was 1-bit, this is 1.58. Okay, in bitnet what they did was they divided it by absolute sum, or absolute max. Yeah, sorry for absolute sum. They divided by absolute max, but here they have done with the help of absolute mean, and that has given a pretty good performance. Okay, and if you are confused by this formula, don't worry, I'm going to show you all the code of how this can be implemented. Okay, this is where the absolute min is divided. Okay, and here is where like you get the weight and you clamp it to -1, 1. Okay, so for quantization also, it is not just into weights. You will also quantize the activation function, which they have followed the same implementation of bitnet, where the clamping happens between the range of -127 to 128, because that is what is the range of 1 byte in int. Okay, so that is the like the math part of how you will quantize a model. Before going on to the code part, I would like to explain the performance which it has shown while their experimentation and all. Then we'll go on with our coding, and then we'll also evaluate the model with some 1 or 2 questions actually. Okay, so now, like I said, the perplexity should be very less. Okay, please keep that in mind. In Llama LLM, they have taken a 700 million parameter model. Okay, 700 million parameter model. The perplexity after pre-training was 12.33, which is not that great, but okay. For 700 million, it's fine. In 700 million of bitnet 1.58, which is, like instead of 16-bit, you are training it in 1.58-bit, which will reduce your memory of almost 3x, because it is 2 GB, this is 0.8 GB, and the latency while inference is 1.18 seconds, 1.18 ms. If it is 700 million parameter in full precision, which is 16, and when you use it in 1.58-bit, it is just 0.96 seconds, and the speed up is approximately 1.23 seconds. 3x, sorry. But the thing which very much fascinated me was this one. when you increase the parameter of the model, right, that is where you get the best out of BitNet. In 3 billion parameter model, the memory was approximately 8 gigs, and with BitNet, it was just 2 gigs. It is almost 4x. Okay, and the latency was pretty huge actually. It gave 3x speed up, that too in a better performance. Please note this. The perplexity was 10.04 in original pre-training, and here it is 9.91. I accept, um like, probably I don't know if they have used a same data for pre-training or they used the original llama itself. That is one question I have actually, because the original llama was trained in a different data set. Here they might have trained in a different data set, or if they had replicated the same, I guess this is a pretty good revolution. I don't think the people have spoken about 1 bit net or bit 1.58 bit net very much, how much it should have been spoken about. Even to be honest with you, I was very skeptical in the initial stages as well. Like, how can you get very good performance just with 1 bit or 1.58 bit? But I'll say, like, now I'll accept that this has very good potential to become the next generation LLM, where every LLM can become 1 bit. That is highly possible right now. Okay. When you're going on to end task, like after fine tuning in 700 million parameter models, if you see the comparison, it was 55 in original, 52 in 1.58, 23, 21.4, 37, 35, 50, or like in every place it is almost 1% or less than 1%. Here it has outperformed. So on an average, we can say 1% performance in decrease in performance for, like 3x speed up, reduction of memory in 3x again, and you're compromising 1% of your performance, and I'll take that on any day actually. But again, the interesting part is when you go for 3 billion models. Here you can see it is very close, like less than 1% of difference. At some point of time, even this has outperformed um the original model. Here you can see it is 62.1, 61.4, 25.6, 28.3, 43.3, 42.9, 61.8, 61.5, 24.6, 26.6. On an average, the original LLM is 49.7 and this one is 50.2, which means it has outperformed with just 1 bit. That is too good for me actually. And here, while training, right, the batch size which they were using for Llama LLM, which in 70 billion model was 16, and with 70 billion on 1.58 bit net, they were able to train it with 176 batch size, and the throughput was 3000 tokens, which is almost 10x actually. This helps a lot in pre-training. I'll be very honest with you. Like, the pre-training is so hard because it takes a long time, but when you can have this much large batch size and this good throughput for just 1 or 2%, even I'll take 5% accuracy compromising, like I can train it for longer time still. This is pretty good. Like, we might see a lot of good LLMs coming up hereafter. Okay, I'm not going to go into these because I've already said, like, it is saving a lot of energy, your throughput is high, your memory is very much reduced. We have seen all of those now. Okay, the energy cost here you can see, like, it is 70 times lesser actually than the original model. Okay, and when they did this bitnet on stable LM 3 billion with 2 trillion tokens of pre-training, it gave an average of 75% performance. That is, again, like, on par with industry, I'll say. Okay, so here is where we have a conclusion, probably, in a way. Okay, bitnet is enabling a new scaling law with respect to model performance in inference. 13 billion, it is more efficient, like in every place, like it is more efficient. 13 billion is more efficient than 3 billion floor pressure 16 in terms of latency, memory usage, and energy consumption. You need to note this point. This is 13 billion, that is 3 billion. Now you might think, wasn't 13 billion version, this is 3 billion. But when you go into float version 16, it is increasing your size. But when you are having it in 1 bit, right, you have the leisure of increasing the performance with having large number of parameters. That is what they're trying to say. See here, memory usage of 13 billion model is higher than a 70 billion model when you train it with BitNet. That is what is the highlight of this paper. Probably I like this section of this paper very much. It gives a new way or a new perspective for us to see. Probably this is the way forward. I don't know. Let's see about that. And I'm waiting for those to like give some mixture of expert model, because I think that also brings out the potential of this one bit a lot. So let's see how that goes. And that is about the paper. Now coming on to the code. Okay, I have already done the pre-training. Yeah. Here is the code, and don't worry, guys. All you need to do is give your model name, and you'll be able to fine tune. Sorry, pre-train rather. Yeah. The thing is, you would need your parameters. Okay. So here, these are some parameters which is required. I'll explain all of those parameters. Okay. First, for model, I took. You can take any llama to 7 billion. Okay. I took this LLM because still there are a lot of people who don't have access to llama to 7 billion. So I took this new service llama to 7 billion. Okay. Because anyway, we are going to pre-train this model completely. Okay, so it doesn't matter which you use. This is just to get your configuration. Okay, so you're gonna get the llama to 7 billion, and now to pre-train, it is gonna take a long time. You might have some memory issues when you are pre-training a 7 billion model, right? So I'm gonna reduce it to 70 million, and you will be shocked when you see a performance of a 70 million parameter model, that too in one bit. Okay, so the head is 6. Okay, like the number of attention head is 6. For a comparison, I'll also show you the original configuration. Okay, so the original configuration is that you'll have where is the heads? Yeah, you'll have 32 heads. Here we'll have 6 heads and 32 layers. Instead of that, we'll have 6 layers, and the intermediate size, which is your hidden size, is 4096 in original model, and we are gonna have it 4096 in original model, 768 in our model, and your intermediate size is 11,000, and here we are having 1024. Okay, and we are just pre-training it with 256 length only. They trained it with 4096. In any way, this is very, 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 very less in comparison with the original model, no doubt. Okay, there is no two ways about this. This is a very, very small model. Okay, if you want to put it SLM in the way people call it now, this is an SLM. So next, what you need to do is give your Hugging Face token here, and also a 1 dB token, because just give me a minute. Yeah, so with 1 dB only, you will have this kind of a dashboard. Okay, so that you can also create your own report here, and it will create a report and give you, so that you can also see how it went. Because see, when you're doing pre-training, right, you can't keep on monitoring it. So when you have a report like this, it will be very helpful for you to monitor the performance of the LLM while pre-training. Okay, you can still go for TensorBoard, but for TensorBoard it is pretty harder when you do it. But with 1 dB, it is very good actually. Okay, so I'll suggest 1 dB. Just create an account in 1 dB and have an API, and then you can provide your API key here. And for dataset, we are using a dataset from Abidin. Actually, this is from Abidin himself. He is the one who made the implementation first, and I also did this implementation referring his implementation only. Okay, and this is the pre-training dataset. Okay, so here it is. Here is an extract web page, and based on this, it will complete. This is completely a subset of the original dataset of Cosmopedia. Cosmopedia is a highly synthetic data, not synthetic data, like high quality pre-training data, if you want to put that way. It's not like a random data which you'll get like a C4 data and all. It is Cosmopedia is a data from Hugging Face themselves, and here it is a subset, like it is a 100k subset. If you still pre-train this with this complete data set, right, you will get a very good performance. Okay, and the batch size here I kept is 16, and Still I had a lot of GPU, like, when I kept it for 16, I got probably 5 to 6 GB consumption. Even if I had 32, I would have been able to pre-train. But if it was, 16-bit, I wouldn't have been able to, like even use 8 as a batch size. That is what is very good when you use 1-bit LLM pre-training. And the learning rate I'm keeping is 1.5 E minus 4 and epochs is 2. Just I've kept for 2 epochs. I didn't even do it for 2 epochs again. Okay. Now, these are the parameters. Now parameters is done. Okay. First, you need to install datasets 1DB and accelerate, because transformers will be defaultly installed in your Colab. Okay. Again, I did this with normal free Colab, which means you can also do it. Okay. I'll also give this notebook so that you can just run this with yourself. Okay. So here we are also calling, this is very important. Right now, this is for Llama, but if you need, let me know. We'll replicate this specific thing again for Mistral. Okay. We'll replicate this. Okay. So right now this is for Llama. In modeling Llama, we are calling all the layers. From transformers, we are taking auto tokenizer, auto config, Llama for causal LLM, data collator. Again, we need data collator for language modeling, trainer and training argument. Everything is taken. Okay. Next, we are loading the dataset with the help of load dataset. From Hugging Face Hub, we are importing login so that we can log in into the hub 1DB so that we can log the performance into the dashboard. And from Hugging Face Hub, we are also using like importing create repo and HF API so that we can push our models. Okay. There are two quantization methods, like I said. One is activation quantization and then there is weight quantization. Both are almost similar. Okay. The only difference here is this one. It is dividing by one, like the main difference is it starts with 127 divided by, okay? Because like I said, the range they are looking on to is within 127 to minus 128, or rather minus 128 to 127, because that is the range for 8-bit, if I'm not wrong. Yeah, for a byte, I think it is minus 128 to 127. And it is absolute max here, where they are taking the value at the last dimension and they are clamping it, okay, with the min value to be 1e minus 5. Because when you're dividing with 127, right, it is going to be too huge. If you have it as probably minus 1 and all, like it will be very less. So they are clamping it with 1e minus 5. So what they'll do is, this is your scaling value, like how much you want to scale the value of your input, which you send to the activation function. Okay. So once you give the value, which is your tensor here, input tensor or input token, it will be scaled with this parameter and you will round off this value. Let's say it is 1.58, it will become 2. Okay. And then you'll clamp it within minus 128 to 127. And then again, you will scale it. You will divide it with the scale. If you take these alone, right, it will be 128, 127 whole values. And then you are scaling it so that it will be very less. Okay. Again, in the weight also, the same process is repeated. You are clamping it to 1 with the minimum to be 1e minus 5 again. Minus 1 to 1 is the range. Here, instead of taking the absolute max, you are taking absolute mean. That's all. Okay. This is the difference. So in linear, or sorry, in 1-bit, like what and all you'll convert as linear is your linear layers. Okay. Your linear layers alone will be converted into 1-bit. So when you get the weight, you'll take the RMS norm and all. So once you normalize your tensor, your input tensor, you will quantize the input via sending it to the activation function. Activation function quantization will happen here. And then you'll subtract with X norm, like, the normalized value again. And you will detach it so that no gradient flow happens. Because when you quantize your model, right, with just 1-bit, that too well pre-training, when you see this model, if you at the end print the data type, right, it will be float 32 actually, because this is quantizing while training, not quantizing post training. Okay. So that is the beauty of this model. But to avoid any overflow error, gradient will overflow. Okay. So for that, you will detach this. Similar thing will happen with your weights as well. And then you will do a normal f dot linear. Okay. That is what happens with bit linear. And now we are creating a function called convert to bitnet. Okay, so here you'll go through the modules in it. Okay, so if you print your model, there will be llama attention, there will be your normalization, there will be your MLP, everything will be there, right? So if it is an attention or MLP, you'll go inside that module, and inside that module, wherever there is a linear layer, right, you will convert it into bit linear. That's all. This is the first step. But like I said, we are pre-training, not fine-tuning. Okay, so if you want to use at the later stage, right, like because now we'll pre-train it, but after pre-training you need to use this model in this stage itself, right? So for this, there will be a parameter called copy weights. You can set it to true or false. While setting, you need to set it as false. Okay, so what happens is the child module, which is your original module, let's say it is your QProj layer, the QProj layer weight will be given to the bitlinear QProj weight. Okay, and then it will be like made like 1.58 bit and all. But the thing is, that is only when you are inferencing or probably you're fine tuning and all. But while pre-training, you need just the layer. Okay, the weight should be randomly initialized, and that's why we are setting it to false while pre-training. Okay, this is nothing like it will remove the redundant layer norms and all. That is fine. Okay, this is just to increase the performance fasten it a bit. Okay, so here we are logging into 1 dB, we are loading the data set, we are loading the tokenizer, and here we are taking the tokenizing the input. Okay, so we are not truncating it. The context length is 256. Okay, everything is done, and now we are making a batch out of it. Like, the whole input batch is ready here. I'm not going to go through it because that is very simple. Okay, so once you tokenize the dataset, you are calling the model via configuration, not via auto model for causal LLM. Okay, because like I said, we need the model's layers, not the model, like with weights. So here also we changed the config, right? So we have our own heads, dimensions, values all differed, right? Now what we'll do is we'll first load the model with this config. Okay, auto config from pretrain will take the configuration, and also the context length is changed to 256 here, and the hidden size is your dimension, max position embedding is your dimension, and then your attention is changed, number of hidden layers is changed. Basically you're changing the all config itself, and then you will just create a base model. Like it won't have any weight and all, it will be randomly initialized weight. Your llama model is created, and then you are converting that to bitnet. Okay, that's what is done here. And then your model size is also printed. Okay, so here it is 77.5 million parameter. Okay, so I just kept it as 70 million, but yeah, it is 77 million. Yeah. Okay, so now you'll also create a data collator, and then which means your model is ready, data is ready. Next, you need to set your training arguments and then run it to your trainer. Okay, even though it is pre-training, right? Still you're gonna have your Hugging Face trainer for this. So it is very easy to pre-train. Okay, so I'm gonna show you that also. You are giving an output path where you need to save this model, and the batch size is provided, logging steps, at how much steps you want to log. Since I did a small pre-training, I logged it at 100 steps, but if you want, you can also do it in more number of steps. Gradient accumulation steps is 2, so every 2 steps once back propagation will happen. The number of training epochs is 2. The warm-up decay, weight decay, warm-up steps and weight decay. Warm-up steps means like at 10%, till the 10% of steps, it will be warm-up, like back propagation won't happen. It will just do forward propagation, preparing for the training. And weight decay is 0.01, which will be, like for your updation of your learning rate. And for learning rate scheduler, we are using cosine. Your learning rate is provided already 1.5e minus 4. I set the max steps to 5,000. I just trained it for 5,000 steps. Okay, but if you are doing a real pre-training, take this out, like just comment it. Okay, if you just wanna test this performance like me, uncomment this, but if you want to pre-train fully, just keep it. Okay. And save steps, like at every 25%, I'll save the model, and I'm setting the FP16 to true because the training should be in half precision. And I'm also setting the logger to be 1 dB. Here to the trainer, I'm providing the model, tokenizer, training arguments, data collator, and the data. Finally, we are training it. And here you can see the training token is very less. Actually, we trained it for less number of data. And the tokens were like, the loss was 3.44 only, which is pretty good. And you can save it here. Okay. So when you call this trainer.save model, it will train in your local, save in your local. And here we already gave the path of bitnet news llama 2 in the configuration itself. And when you go into the final model, right, it will be saved. So what we are doing is we are creating a repo in Hugging Face first with the Hugging Face ID, which is provided in here itself. So here it is. Here it is Vasant and slash your new model, which is bitnet news llama 270 million, which is provided in your configuration itself. Okay. So there is where we are saving the model, and report type is model, because we are not saving dataset or evaluation or something like that, right? We are saving the model, so we are keeping it as model. If it is existing, okay, it is fine. If it not, create it. Okay. And for token, we are providing the Hugging Face token, which you would have provided there. Okay. So in that folder, you can upload your model files. Okay. So you can upload the folder, which is here. Obviously, it would have been here if I had not got disconnected. Obviously, my GPU has gone because I did some pre-training, right? It was long time. So yeah, you can just upload your model via this cell. Okay. If you run the cell, it will upload your model, and that is how you will complete your pre-training. Okay. You are taking I'll just summarize it. You are importing your required imports. You are changing the configuration to have a lesser size model. Okay. Lesser parameter model rather, not lesser size. Obviously, when you use 1 bit itself, it's gonna get lesser. So you are creating some functions for quantization of activation and weights, and then you will also change the forward function of the linear itself, and you'll convert the bitnet, convert the model to bitnet with the help of this function. Okay. So for this, what you'll do is first you'll take a configuration of llama 2. You will change the configuration to our configuration, and then you'll create a bare like basement model of llama, and then you'll convert that to bitnet. Then you'll create the data set. You will have your 1 dB and all for logging. Then you'll have your training arguments. Then you'll set up all these to your trainer, send it to your trainer, and then you'll train it. Okay. So that is how your pre-training is done. Okay. With 1 bit. Now, like I said, my pre-training was just 5,000 steps, so there wasn't much to do with that. But I'll say, like, even for 5,000 steps, it was pretty good. And I'm using the model of Abidin himself, where he did the same method, where he trained it for a longer time. Okay, all are same. Okay, so when you call this model, call it via auto model for causal LLM, but you need to convert it to bitnet. Okay, and then you will set copy weights to true here. That is very important. This is inference in 1 bit net, 1 bit net obviously, and the inference, I'll say, it is pretty fast actually. Okay, so for generating 50 tokens, I'll say it was pretty huge. Like, it was it was so fast. I asked, what is machine learning in today's digital age? Machine learning has become a crucial aspect of our lives with the increasing popularity of machine learning. It is saying some random things, but it was at least relevant. Okay, it was to train it for very less number of time and get this good result in 70 million parameters. I'll say, like, it is pretty huge, because I have seen 3 billion parameters pre-training and all not going very well actually. So I'll say this is good. So this is his pre-training. Okay, he has got the loss in around 2 point something loss. Okay, he trained it with 25,000 steps probably. Okay, this is his report. Okay, and he has himself said that this is just an experiment, you will not get good results. Even that's what I'm saying, like you won't get ready-made good result. But if you train this for a long time, like if you consider this whole data set of Hugging Face, Cosmopedia, and if you train it for so long, surely I'll say like you'll get a very good performance, because that is what we saw in the paper, right? And this is how you can also infer. So in this video I showed you about the paper being explained of how one bit net works, and then we saw how you can pre-train the model by converting your model in 1 bit, and then we also saw how you can inference your model in 1 bit net. Guys, this I'm the first person to upload about this in YouTube, so please hit the like button. If you haven't subscribed, please subscribe, because it helps me a lot to create unique contents like this in YouTube and give you so much free content. And if you want to join and support the channel even more, I'll have some exclusive things for you. There is membership available, so you can also join the membership. um and share this video with your friends, because I feel this is probably the next revolution gonna come up in the field of LLM, moving towards, like, less parameter, not less parameter, large parameter, but in less bit, because we are now moving on to SLMs, with less number of parameter getting very good performance. Why not get bigger parameters with lesser number of bits? Again, you're keeping your memory reduced, your inference time reduced, your energy consumption reduced. You're gonna get better performance. Why not? So this could be a way forward. There is a great potential for this. So that is what is my conclusion in this video. It is an amazing paper. It was an amazing read for me in the weekend. So what could be the way forward in this? See, the thing is, now we just did a small pre-training, right? You can do a complete pre-training of this Cosmopedia dataset itself, because that is a pretty good dataset. You can pre-train it completely and then do a fine-tuning, and you can use it for real-time use cases as well. So if you are interested to do that, please let me know in the comment section. I'll somehow try to do it, like, take a run pod server, probably run on it for a longer time. Probably it will cost me a fortune for sure, but yeah, I'll try my best to do that. At least to the subset of Cosmopedia 100K dataset, I'll try to do on that at least, so that we can see how much this can be done. Okay, so let me know your thoughts on that also in the comment section. But that will take a bit long, because I need to earn something to invest on runpod. Okay, so that could be a way forward. Like, you can train it for a longer time, fine tune it, and then you can use it for real world as well. That is the way forward, I think, with this bitnet model which we saw today. So yeah, guys, that's it for this video. I'll see you all in the next video. Until then, cheers.